Okay, so let's get started. And today I want to give a proof of Poincare duality. Okay, so Poincare duality says that the ordinary cohomology of an oriented manifold is isomorphic to the dual of the cohomology with compact support in the complementary dimension. And this duality comes from a pairing, okay? So it is the Poincare duality pairing. Okay. And what we do is we pair a form with no condition, with a form with compact support in the complementary dimension, and then we integrate. Now, in order to integrate, you need the manifold to be oriented. Let M be an oriented manifold. Without boundary. Okay, and then you consider the pairing. So you take a closed K form, pair with closed N minus K form with compact support. By integrating the wedge product, okay? So if you wedge them, then it's a top form. And I'll show that it still has compact support so that you can integrate and you get a real number. Okay, okay, so omega wedge tall has compact support because the support of the wedge product right? It's contained in the intersection of the supports. And so that's contained in the support of tall. But we know that tall has compact support. And the support is always closed. So you have a closed subset of a compact set, therefore it's compact. Okay? So as long as one of the two forms has compact support, then you can integrate the wedge product. Okay. Okay, that's the first observation. And the second observation is that if you take a closed form and you wedge it with an exact form, then what kind of form do you get? Closed wedge exact is closed wedge D of something. So What do you think it should be? It should be exact because that's the same as D of closed wedge something, right? Oh, there might be a sign, okay? Because when you take D of a wedge product, you have this anti-derivation rule. So you get D of closed, that's 0. So the first term is 0. Then you get a sign times closed wedge exact, okay? So closed wedge exact is always exact. And if you integrate a closed form, wedge in exact form, then you're integrating an exact form, so D of something. And by Stokes theorem, this is the integral over the boundary of something. But, you know, our manifold has no boundary, okay? So this will be 0, okay? Yeah. Okay. What this says is that here, you know, this integral, it will induce a map on the closed form cross the quotient, right? You can, because the exact forms will give you 0. Therefore, you will induce a map on the quotient of closed wedge over exact, and that's the cohomology. Well, of course, you know, it goes the other way too. The integral of an exact form wedge a closed form is also 0. And so, so this map, yeah, so the integration map, this map, let's call it star. So the integration map in star induces a map on the closed forms over the exact forms across the closed forms with compact support over the exact forms with compact support. And this is the cohomology of M. This is the cohomology with compact support of M. Okay. Therefore, you have a pairing on the cohomology groups. And the theorem, which is Poincare duality, let me just put it over here, is that it's a non-degenerate pairing. So that, you know, yeah, so this pairing is non-degenerate. Okay. So last time I defined what non-degenerate means, right? It means like if you get zero, like if you take something here and then you get zero for everything in the second factor, then the first one is zero. Okay, now the hypothesis is that M is an oriented manifold without boundary for an oriented N manifold M without boundary. Okay, this is non-degenerate. And last time we showed that when you have a non-degenerate pairing, then the left map and the right maps are isomorphism. So the left map is the map that goes from the first factor to the dual of the second factor. Okay? So we know that the left map is an isomorphism. And so is the right map. Okay? But just knowing that the left map is an isomorphism, gives you this upside down symmetry, right? Because the dual of a vector space has the same dimension as the vector space. And so that says the dimension in degree K of M is the same as the dimension in degree M minus K with compact support of M. Okay? Yeah. All right. Okay. So that's what we want to prove today. Okay. Now, yeah. So like I have to do some setups. I mean the proof actually turns out it's not difficult. Yeah, but you have to do some setups. Okay. So let's first look at diagrams of pairings. Okay. All right. Okay, so let's say I have a pairing A cross B to R. Let's call it C. Yeah, and I have another pairing C cross D to R. Okay? A pairing is just a bilinear map. Okay? And I have a map from A to C, a linear map, and a map G from D to B. Okay? So I get a diagram like this, and I say that the diagram is commutative if whenever you take an A here in A, oh yeah, I have this, let's not call this vector space D, because we often use D for a differential operator. So let's call it E, okay? And I have an E here, okay? Then you see, you can take A, map it here, so you have f of A, and then you can pair it with E, right? So you can take f of a, pair it with e using psi, and you get a real number. Okay, but you can also do it the other way. You can go down this way. You can pair A with G of E and then get a real number. So I can also pair A with G of E using phi and I get a real number. If these two numbers are equal, then I say that the diagram is commutative. Okay. Okay. Well, it turns out that a commutative diagram of pairings is equivalent to a commutative diagram of linear maps. Okay. So whenever you have a pairing, you have a left map. So I have a map A to the dual of B. Okay. So that's a left map. And then I also have a left map here for psi. So C goes into E dual. And I have a map F from A to C. Okay. Now G is a linear map from E to B. So it induces a map on the dual going the other way. So we have a map this way that is G dual. And then the theorem is that the pairing diagram is commutative if and only if this is commutative. This is just a diagram of vector spaces. So this diagram is commutative if and only if the pairing diagram is commutative. Okay, and let's prove this. Okay, so okay, so what does it mean for this diagram to be commutative? So it means for all A in A, if you go this way, so f of A, let's see, this is psi of L, right? This map. F of A followed by psi of L should be equal to doing it the other way. But maybe I will do it the other way first. So if I go this way, then G dual composed with phi L of A, okay, should be equal to going the other way. And this is G dual of the left map of A, that is phi of A, and then apply to some argument, right? The argument is in B, okay? So that's how you, this is a linear map on B, okay? And then the dual map is simply the composition So it means that you first apply G to the argument. So you apply G, okay, to the argument, and then you apply this linear map. Okay? So that's going one way. Uh-huh. And then going the other way would be psi composed with F, psi L composed with F of A, and that is psi L of F of A, and that is psi of F of A, and then with an argument coming from E. Okay? Yeah. And oh, right. And you see that this condition is the same as this condition, right? Yeah. If you put an E here, then you get precisely the commutativity of the pairing. Okay. Yeah. So yeah. So that's the proof. Yeah. So instead of let me see, checking that a diagram of vector spaces is commutative, we can check that a diagram of pairings is commutative. Okay? And so what we are going to do is we're going to pair our two Mayer-Vietoris sequences. Okay? For de Rham cohomology, you have a Mayer-Vietoris sequence. For cohomology with compact support, you have another Mayer-Vietoris sequence, and you can pair them. Let's see. Let's keep that. And then this. Okay. You see, the proof of Poincare duality is going to be by induction on the number of open sets in a good cover. Oh, just a minute. Yeah, I that's right. I need another hypothesis. Here is a statement of Poincare duality. So of course, you have to have an oriented manifold without boundary so that the Poincare duality pairing is defined. But for the proof to work, because we're going to do it on induction on the number of open sets of a good cover, you need to have finitely many open sets in the good cover. So actually, I need an additional hypothesis here. So this is the theorem, right? So theorem, Poincare duality for an oriented N manifold without boundary, and I should say it's of finite type. That means it has a finite good cover. Okay, so you need that hypothesis in order to do your induction. So the theorem is for an oriented M manifold M of finite type without boundary, the Poincare duality pairing is non-degenerate. Okay? And then you get an isomorphism between de Rham cohomology and cohomology with compact support in the complementary dimension. Okay, and the way we carry out the induction is to use the Mayer-Vietoris sequence. Okay. So let UV be open sets in an oriented manifold M. Yeah, like just to pair them, just to pair them, you don't need any more hypothesis. Right, and so you, okay, so you have this Mayer-Vietoris sequence, HK from the union to HK of U direct sum HK of V to HK of the intersection to HK plus 1 of the union, right? And this map we call I star, and this is J star. And then we have the one with compact support going in the opposite direction. H M minus K of the intersection going into H M minus K of U plus H M minus K of B, okay, going into H M minus K with compact support of the union. Okay, yeah, so we've got these two Mayer-Vietoris sequences. Now this map is the boundary map, D star. This is the boundary map, D lower star. And this is J lower star, right? And this is I lower star, okay? And okay, so these have complementary dimensions and we can pair them to get R. Now, well, this part, okay, so the way you pair them is you integrate over the union, okay? Now you can pair this factor with this factor, you know, so you integrate over U, and here you integrate over V, and then you get two real numbers, you add them, then you get a real number. Okay? And here you integrate over the intersection. Here you integrate over the union. All right, yeah. So you get a diagram of pairings by pairing these two Mayer-Vietoris sequences. We have to know what these maps are. Now, can you remind me what is this map, I lower star? What is I lower star? From the union to the individual open sets. It's what? It's a restriction, right? Yeah, so this map is the restriction. And what is this map? It's a difference of the restrictions, okay? You have to restrict to the intersection and then take the difference. So it is a difference of the restrictions. And that's a boundary map. And what is this map, J lower star? It's a signed inclusion. So, you know, you include by extension by 0, and you put a sign on the first factor. This is the sign inclusion. And what is this map? It's the sum. Yeah. Okay. All right. So let's review what these two boundary maps are. Okay. Okay. Yeah. So let's see. Okay. Okay, so let's first, let me see where, yeah, here. Okay, so let's first review the construction of the upper star in ordinary cohomology. All right. So, do you remember how the boundary is defined in general in a cochain, complex? Like, if you have to like do a motion, what kind of motion would you do? Yeah, use your arm to show me how you would get the boundary map. Is it like this? Yeah, so do it. Yeah, let me see. Let me see. Like, is it like this? Is it like this? Is it like this? What do you do to get the boundary? Didn't you do it? Right. Yeah. So you do like this, right? A zigzag. So you start with something here. So a form, a K form in the intersection, right? And the short, exact Mayer-Vietoris sequence comes from a K form on U and a K form on V, because you're going to take the difference of these two things. So you start with something here, and it comes from something here, and then you take D. So you get omega K plus 1, U plus omega K plus 1V. Okay, and because you start with a closed form, it goes to 0. So this here will go to 0. So it has to come from something here, right? Yeah, that's the diagram, okay? And yeah, so you start with something here. Okay, so you have omega, but it's closed. And it comes from a form on U and a form on V whose difference is omega. Okay? And do you remember the two forms that map to omega? What is the form on U? Oh, well, you have to choose a partition of unity. Right. You have to, yeah. Choose a C infinity partition of 1, rho U, rho V, subordinate to UV. Okay. Then if you start with the closed form, it is going to come from a form on U. Now the form on U is multiplied by the partition of unity on the other open set. So it's rho V omega, okay, with a minus sign, and then rho U omega, okay? This is what we showed before. Because if you take the difference, then you have rho U plus rho V, and you'll get omega, okay? And you have to use the partition of unity on the other open set, in order to, get this to be defined on U. You should review what we did before, all right? So that's, these are the two forms that map to omega. And then it's gonna go to D of these two forms minus the rho V omega, the rho U omega. And we know that there's a form that has to map there, and that form is the upper star omega, okay? And this map is a restriction. So the upper star omega is the form on the union such that restricted to U is this, the upper star omega is equal to minus d rho V omega on U, and it's equal to d rho U omega on V, okay? So that is the explicit description of the upper star omega. And now let's do the lower star omega. I don't want to erase my diagram of the pairings. So let's do it over here. Construction of the lower star from H n minus k minus 1 with compact support. of the union to H m minus k with compact support of the intersection. Okay. And now here, let's see the short exact sequence of the short exact sequence of forms. It's yeah. So yeah. So you have omega m minus k minus 1 with compact support of the union. Let me see. This map is a difference. This map is a restriction. Okay. And this is going to come from the sum, right? So it's omega m minus k minus 1 of u plus omega m minus k minus 1 of v, and this is the sum. And then we take d, and then this should come from omega m minus k of the intersection. Okay, and this should be the sign inclusion. Yeah. Okay. So we start with Paul, which is closed. And it comes from the sum of a form on U and a form on V. Okay. So do you remember the formulas for the two forms? The form on U. Okay, so if you look back, it's going to be rho U of tau and rho V of tau. Now, actually, rho U of tau, yeah, is the first factor. You see why? I mean, tau is already defined on the intersection. No, tau is defined on the union. Rho U is defined everywhere. So you don't have to worry about, the domain. I mean, rho U of tau, it will be defined on the union. Okay? And it will have support in U. Yeah, you see, yeah, it's easier now because like over here, you have to extend a function from an intersection to a larger set, and that might not be possible if your function blows up. Okay? But here you're starting with a function that's defined on a larger set, so you're not extending it, and so it's it's easier. You just multiply by rho U and rho V, and their sum will be tau. Okay, and then you take d of this, so you get d rho U tau, d rho V tau. Okay, now you know that rho U tau plus rho V tau is tau because you have a partition of unity And so if you take D of both sides, you'll get D tall, which is 0, since tall is closed. And this implies that D rho V tall is minus D rho U tall. Okay. And so that's what you define to be your D lower star of tall. Okay. You see, because, yeah, D lower star of tall. Uh-huh. Uh-huh. You know, this map is the sign inclusion. Okay. So you define it to be, it's actually defined everywhere, but you just restrict it to the intersection. Okay. And it's, yeah, so you see when you do the sign inclusion, you know, okay, the second factor is just D rho V tall. And the first factor should be, it's negative, right? The negative of this guy on U, and so the negative of the negative will be positive, okay? So this is the construction of the lower star. All right, so now we understand all the maps in this pairing diagram. And yeah, so what we want to show now is that, you know, first of all, this is a commutative diagram, or commutative up to sign. And that would mean that the diagram of linear maps to the dual, you know, is commutative. And then, you know, we'll show that like Poincare duality for U, V, and the intersection will imply Poincare duality for the union. And then we can do our induction that way. Okay, let's take a break for 10 minutes, and then we'll continue. Okay, I just got a question about the hypothesis of Poincare duality. You know, I said that we have to assume that M has finite type so that we can carry out the induction proof. And the question was that, you know, if M is not of finite type, whether Poincare duality is still true, you know, but maybe with a different proof. And the fact is that if it's not a finite type, then you don't know that the cohomology is finite dimensional. And so, you know, you cannot state Poincare duality. Okay? So you need finite type for two reasons. The first one is to guarantee that the cohomology is finite dimensional so that you can, you know, state the theorem. And the second one is the proof that, you know, I will be giving. Now, you know, this morning, while I was going through my notes, I noticed that there was a gap, and that is, in the proof, I actually needed this D upper star omega to have support in the intersection. Now, D upper star of omega is a form on the union. And the proof actually requires that it has support in the intersection, even though it's defined on the union. And I couldn't You know, earlier I had some proof of that, but it was fairly complicated, and I didn't think that I could do it today. But you know, just now I realized that yeah, I could actually. It's actually fairly simple to prove. Yeah, makes me think that maybe you know there is a God that's protecting me because every time I get into a bind, then somehow you know the solution suggests itself. Yeah, yeah. I used to pray, you know, to Guan Yin Pusa when I was taking before I took an exam when I was in elementary school. And I think she always helped me, and I think she's still helping me. So, yeah, we need this proposition that the upper star, although defined on the union, has support in the intersection. Okay. Yeah. So let's see. Proposition. Uh-huh. Um, yeah, for omega in so yeah, for this class in HK of the intersection, the upper star of omega in HK plus 1 of the union has support in the intersection. Okay, so, well, the upper star omega is defined by two formulas. So it's minus v rho v omega on u. Mhm. And the support of rho v omega, let's see. So it is in the support of rho v intersect the support of omega. So it is in the support of omega. And by hypothesis, yeah, omega is in here in the intersection. So the support of omega is in the intersection. And the thing about D is that D is support decreasing. Um, so yeah, so D rho V omega also has support in the intersection. Okay? And therefore, D star omega has, when it's defined on U, has support in the intersection. And when it's defined on V, it's the same argument, right? Yeah. So, yeah, similarly, for D star of omega on V. Okay. Yeah. Okay. Uh-huh. Uh, okay. So what we want to prove now is that um, these three squares are all commutative. They're commutative diagrams of pairings. 1, 2, 3. Commutative up to sign. Okay. So in the homework, I asked you to show that 1 and 2 are commutative up to sign. Actually, for 1 and 2, they are commutative. Okay? But 3 is commutative up to sign. Okay, so let's just check 3. All right. Uh-huh. Let's call this a proposition. And maybe I'll call this diagram the Mayer-Vietoris diagram. So the Mayer-Vietoris diagram is commutative up to sign. Okay. So actually, 1 and 2 are commutative on the nodes without the sign, or the sign is positive. But 3 does have a sign. Okay. All right. So what do we have to show? What we have to show is that, you know, if you start with a omega here, and a tau here, right? Then going around the diagram, you know, in the two ways, will give you an equality up to sign. Yeah. So let's, okay, so let's write down what we have to show. So for omega in HK of the intersection and tau in H m minus k minus 1 with compact support of the union, going one way, let me see, if I go that way, that means I have to go, so if I do d star of omega, wedge with tau, and then integrate on the union, that should be equal to, okay, going this way would be omega wedge the lower star of tau, and then I integrate on the intersection. Okay? So that's what we need to show with a question mark there. And yeah, so let's do the left-hand side. This is, now, I just proved that the upper star of omega is supported in the intersection. Okay, so it's 0 outside the intersection. And that means this integral on the union is actually the same as the integral on the intersection. And now on the intersection, I can use either formula for the upper star. And yes, it's right here. I can use either of the formula. So I'll use this one without the sign. So d rho u omega wedge tau on the intersection, okay? And because tau is closed, right? So this is going to be the same as, let me see, d rho u omega wedge tau. Because I get, right, d rho u omega wedge tau, and the other term will have a d tau in it, that would be 0. Okay, so I get this. That's the left-hand side. Okay? And now let's do the right-hand side. Um, so the right-hand side is the integral of omega wedge d lower star tau on the intersection. Now d lower star tau is right here. It's minus d rho u omega. So put the minus sign there, rho u d rho u omega tau, d rho u tau. Okay. And okay, because omega is closed, so this is minus, I can put a d in the front. But, okay, so d omega will be 0, and then the second term should have a sign, and that sign should be -1 to the degree of omega. Okay? Okay, that's the right-hand side. And okay, rho u is just a function, right? So I can move it around. And so I can write this as d of rho u omega wedge. Yeah, rho u omega wedge tau. Okay. Yeah, so that's the same as this, up to this sign. Yeah. Okay. And that proves that the third square is commutative up to sign. Okay. And then we proved lemma earlier that, you know, if you have a commutative diagram of pairings, then you have a commutative diagram of linear maps, you know, to the dual. And so let's see. So let's see what we get. Yeah. Thus, no. Okay, I don't want to erase that. So you know, I think I need a lot of space. So so I think I need to use this side of the board. Uh, maybe I call it a proposition before we get a commutative diagram of linear maps. So it would go from HK of U intersection V to the dual of HM minus K with compact support of the intersection. And then, yeah, when you take the dual, you reverse the direction of the map. You know, I think it's only in algebraic topology that you have to spend a lot of time just writing these diagrams. Okay, uh, this is the dual there. J. All right, so we have a commutative diagram like this. And so if you have Poincare duality for UV and the intersection, it would say that this is an isomorphism, right? This is an isomorphism. Oh, here I'm using the fact that the dual of the direct sum is the direct sum of the dual. Yeah? And then this is the isomorphism. And the next one, you know, it's also an isomorphism. So you get the two maps on either side of the cohomology of the union being isomorphisms. And then there's this 5 lemma, which I asked you to prove in the homework. You will get this center map to be an isomorphism also. So Poincare duality for U intersection V by the 5 lemma will imply Poincare duality for the union. And so you can start doing induction. Now the base case, well, so you assume that M has a good cover with R open sets, and you induct on the number of elements in this good cover So when R is 1, that's when you have just one open set. So M is just U1, and that's diffeomorphic to Rn. And well, it's easy to check that Poincare duality holds for Rn, because you know what the cohomology groups are. Okay? So Poincare duality holds. And then you just induct on the number of open sets. The way we did it for finite dimensionality. So yeah. So by inducting on R, Poincare duality follows. Okay? Yeah. Okay. Yeah. Okay, so this method of proof that uses induction on the number of open sets in a good cover and the Mayer-Vietoris sequence is a very useful argument. We used it to prove the finite dimensionality of the Ram cohomology. We just use it to prove Poincare duality. Next time we will use it to prove Punneth's formula, which gives you the cohomology of the Cartesian product of two manifolds. Okay? Yeah, and it can prove some other theorems too. The Thom isomorphism and the Leray-Hirsch theorem, you know. So we'll do that next time, okay? So I'm gonna end here today.